I know that you don't have another track to go, but I really appreciate you coming here. Today I'm going to talk about something that I'm quite vocal about because I learned the hard way how important tests are. Some super quick words about me. I'm part of this telco team at Red Hat. I work on networking features of the Kubernetes platform. So I'm split between system programming, networking, and Kubernetes controllers implemented in Go. And I also maintain the MetaDB project. Those are my handles. If you want to reach me out, feel free. I'll try to reply. So let's start with something broad. Why do we need tests in first instance? And the reason is that our programs are never done. We always change them. We keep changing them because of many reasons. We need to add new features because our users like our software and they ask us to make it do different things. We need to fix bugs. We need to do refactoring and reduce the technical debt. And we need to make things faster. So when we do a change, what do we test? We have a behavior in place. That is what our users are expecting. And then we have the new behavior that we are adding. And testing only that new behavior is a recipe for disaster. So I like a lot this quote by Michael Feathers. Changes in a system can be made in two primary ways. One is edit and pray that we don't break anything, and cover and modify. So cover with test and change the rest, making sure that the behavior is not changing. And unfortunately, and I can confirm that, edit and pray is pretty much the industry standard. So if you don't trust me yet, let's discuss about how fixing a bug costs. And there are a lot of articles saying that it's 1,000 more costly fixing a bug in production than in our local environment. I don't have the exact figure, but it's clear that fixing a bug in our safe environment, in our laptop, is much easier than fixing that when a customer is reporting something that is not working as expected, and we have all the pressure to fix it. This is one of the most notable cases where software bug cost a lot, where a bank lost a lot of money in a few seconds because of some bug. So we need to have tests result in having a better quality of our product. They make sure that our current behavior doesn't regress. We document the instrumented units through tests. Normally, code that is testable also is better written than code that is not testable and allows us to continuously instrument our software through CI. There are many kinds of tests. I'm going to describe very quickly some differences between unit tests and integration tests. So unit tests are testing a very specific part of our code base, a unit. They are deterministic, they are meant to be quick, and they are meant to run on our laptop. On the other side, integration tests are testing a system as a whole or a part of the system. They are more adherent to reality because they are testing the real thing altogether, but they are slow, they may not run on our laptop, and it's really hard to get them right because you have an external state that you depend on, you have many moving parts, and they are harder to master. So this talk is going to be more or less about unit tests to some extent. What is a unit test? There is no clear definition. There are many definitions of unit tests, but there are some common traits that you can say they respect. They are low level, they focus on a small part of the system, they are written by programmers, they are faster than normal tests, and they do not depend on external systems. So we can have many of them, and we can run them very quickly. So let's start with what this talk is about, which is unit testing Go. If you come to Go from another language, you may know that there are a ton of frameworks that enable testing for those other languages. I don't know if these are outdated anymore because it's been a while since I write something that is not good. But in Go, you can go very, very far with what the standard library provides you. So let's start with the basics. You have a simple function. You can write a test function for that. A test must have this structure. It must start with the test. It has to have this parameter. It must be implemented in _test.go file that is in the same package. And you can do a few things with that package. You can run the test and see if it's passing, or if it fails, it will give you some errors. One thing that you can do with Go is to either have your test part of your package, so you can access internal symbols of the package, or you can name your test after the main package _test, so you can somehow emulate a client of your package. So these allow you to focus only on the behavior that your package is exposing. Your tests will be less brittle, maybe, because the main behavior is less likely to change. But of course, sometimes you might have some complex logic that is hidden and that you want to test. So there is no rule of thumb. Sometimes it's useful to access the internal symbols. Subtests are a nice feature of the Go testing library. They basically allow us to group a set of tests under the same umbrella. So you have these t.run subtests that belong to the main parent test that is wrapping them, and they are useful for a few reasons. You have better control on what you run, because by running only the main test, which can be testing a feature, and you want to run only that, you can run the main test, and it will run the subtests. It's a nice way to have your test code organized and to have some shared code between those subtests. For example, it enables the well-known setup and teardown pattern that is common in many other testing frameworks. And it's an easier way to enable parallel execution. So this is an example where we have some shared code. Here we set up something. We call this t.cleanup function that is invoked after the test execution. And then we have our test. So pretty easy. We can enable parallel execution and this is not a thing of subtests, but I think all the tests of the same category might be running in parallel or not, so it goes together with subtests. By doing this, all the subtests will be run in a separate Go routine. The parent test will wait until all the children are done. There is also another variant which feels a bit lower level, which is using test main. You can have one of those per package. It feels, again, like more an implementation hook, to the point that you are calling m.run manually, and you have to return the exit code manually through os.exit. But depending on the use case, it might be useful. Table tests. I know that the title of this talk is Beyond Table Tests, but we are at 10 minutes, so I still have some material after this. So, table tests are not something new, but I think it's something that is pretty idiomatic in Go, and they are a way to define a test through some properties, the parameters, the expected behavior, and then we can describe them, and then we can have our common code, and then we have the execution of each test by iterating over those tests. And it's clear that by using this definition, enhancing our coverage, enhancing the scope of our test is just adding a new line on this set of tests. So, and again, unit tests are meant to be run, so you can possibly add a lot of them. How do we control test execution? You, of course, might need to run the whole set of tests, but you might need to focus only on what you are changing, so you can specify the dash run flag, which takes a regular expression, and it will run only the test matching that name. Testing.short is something useful if you are mixing integration tests and unit tests all together, because it's something that is built in, or you can use build tags. Okay, so now I'm going to talk about the test fixtures. A test fixture is something that is pre-built and that is used to test our software, and there are some cases where this comes pretty handy. Think about when you want some artifacts to run some tests that are instrumenting parsing of files or images or some content of the DB. And putting them in your code base, on your test code base, feels a bit clunky. You have these big strings. So we can leverage the fact that the content of test data is ignored at compile time, and when we run go test, the current folder is matching the test file. So let's say that you have something like this, your package, your test package, and your test data. You can easily access the content of that folder that is not going to be part of your binary, and it's much easier and much cleaner to test. Another common pattern that leverages fixtures is golden files. It's, again, something that is heavily or is used quite often in Go tests. Basically, the idea is that if you are generating some output, asserting the generated output is tedious. Think about when you have to generate a configuration file from a Go template or some HTML or some JSON output. So instead of having the expected output as part of the test suite, we generate the expected output and we produce it as part of some file that we save that becomes our source of truth. So the workflow is we force the update of these golden files with the current result. We inspect them manually. We look at them. We make sure that they are what we expect. And then we use them afterwards as the source of truth for our subsequent tests. And this is how a test like that looks like. We generate the name of this golden file coming from the test name. If an update flag is set, we write that. Then we read it, regardless of the fact that update flag is set. And then we compare that to our result. And this is how it looks when we run it. So first time the file is not there, our test is going to cry because the file is not there. Then we run with update. So this is when the golden file is generated. We go and we inspect it. We make sure that it's fine, because that's the only quality check that is going to happen to that output. And from that moment on, you can commit it. It can be part of your test suite. And of course, Go test comes with a lot of other features. We have coverage. We have benchmarking. If you realize that you have some functions that is in the hot path because you use pprof, for example, you understand that's a bottleneck. You want to optimize it. You want to make sure that the changes that you are doing are better than before. Go comes with benchmarking support out of the box, and it's pretty handy. Race detector, to understand if you have races among Go routines. You can shuffle the tests. Test helpers are another nice utility. Let's say that you have some util functions and that can fail. by declaring this as a test helper, you can fail directly in the helper definition, and the big difference is that your test code is not be bloated too much with the error check. So you can do this, and when it fails, if you don't declare the helper as test helper, it's gonna fail in the location of the test helper. By declaring it, it's gonna fail in the caller. So it's a fancy trick to have less bloated test body. So now I'm going to talk a bit about how do we make our code testable. We said that we want our test to be fast, to be independent on the execution order, not depending on external systems, repeatable. But we also want to produce nice software that is useful for something. So normally, we need to interact with something else. So an instrumented unit can be stateful. It can be interacting with some external system, which is an API, the operating system, the file system, or the network, and never trust the network. So there are a few options. First option, you come and you need to cover some legacy code. So one possible option is to try to have the business logic separated from the integration glue and have that as a pure function. A pure function is nothing more than something that accepts an input and it always produces the same output. So it doesn't depend on the state, it doesn't depend on the external systems. A very simple example, we have this function. It depends on something external, which is the file system. What we can do is, and in this case, our business logic is very simple. It's just the parsing. So we can separate this. And again, it's not something that I suggest always, but can be a first step. So now our dependency is not an external system, and this can be tested in isolation. Option 2 is override the status. We have some fixed path, for example, and we need to parse it because that's the path of the configuration file. We can move the constant to a variable, and we can have our test swapping it under the hood. So, and this is a common pattern where we save the old path and we restore it after the test execution because maybe some other tests rely on the proper path, or it wants to replace it with something else. But sometimes, and quite often, we can't avoid this interaction. But we want reproducibility, and we want speed and independence from the state. So the proper approach is to introduce test doubles. Test doubles, mocks, there are many ways to name these things. But the idea is to have something that is implementing the behavior of the external unit that we want to test. So let's try to have another example and reintroduce our dependency. This is an external package that calls add over the network. We don't know the behavior. It can fail because our laptop is not connected. So we want to try to replace it. The first option is to have a local variable assigned to that because we can assign variables, functions to variables. And this allows us to do something neat, which is again, we save the old value so that other tests won't be affected. And we replace that with something that we control, that is consistent, and that it will always have the same behavior. And we can also add probes. So we can check how many times this function is called, because our expectation is that our code is called in that. I need to run a bit. This sounds like changing things under the hood, so it's not my favorite way. And the proper way is to use dependency injection. Dependency injection, it's quite famous because of dependency injection frameworks, but the basic idea is that you are passing your dependency from outside. In this case, we are passing our dependency, which is like this add function, from outside. And of course, by doing this, we need to change also the color. So it's a bit more, has a bit more impact. But the idea is that on the test, we can pass the test double of the dependency, and we have control over the behavior. And we can also do that with objects. If our dependency is an object, then we can pass it to the function that is using it. We need to do a bit more. We need to use an interface which represents the behavior of our object. We need to, again, change our calling site. But what we do on the testing side is that now we can have a mock that implements our behavior and that where we control the behavior of it. And we can have probes as well. So, yeah. And this is the test. We inject the test double. We control the behavior. Our test is going to be consistent. And of course, we can also assert the probes. So dependency injection is about injecting dependencies. A dependency can be an object, can be a function. The dependency injected can be, in turn, injected with something else. So in this case, we have an object. We need to inject it. We move it to an interface, and we use the interface instead of the real object. There are libraries to make our life easier, but I'm a fan of using the standard Go library. Do we always need mocks? That's debatable. There are some cases where we have something that are not entirely mocks. We can use real files under test data. There is this Affero package that provides file system implementation, both on leveraging the real file system or memory-based file system. Another thing that is nice in Go when you have networking is that instead of using mocks, you can spinning up a proper server, gRPC, HTTP using the HTTP test package. And this is the approach also taken by Kubernetes, for example. And this runs a real server. So we are testing the whole stack. Last thing that I'm going to talk about very quickly is what I call almost integration tests. So let's say that you are interacting with an external component. Let's say it's a database. It's something that takes a configuration file that you are producing. It's easy to spin it up. The interaction is low level. So writing a mock is risky. Let's take a database. Here we have a getQuantity method is running a query, returning the quantity. We spoke about dependency injection. So let's write a mock. We write the mock. The mock returns the result that we are giving it because we know the behavior that we want to mimic. We test it. It's green. But there was a syntax error. Quantity is misspelled. There are two packages that are quite handy in this case, test containers and Docker test. You can run your dependency in your container. They are quite easy to set up, and they allow us to validate our code against the real thing before going to integration. And this is how it looks like. We spin up the Docker container, and then that's available to our code base. And of course, you now have an external state, so it can be flaky. So you need to be careful enough to do the proper cleanup after each test. So wrapping up, we learned a few things about Go. We learned how to isolate our dependency. We learned how to cross the units across the boundaries. I want to remind you that choosing not to have a test is choosing not to have a guarantee against the behavior. It's not choosing not to have the bug. It's choosing between having the bug when a production bug happens or when the software fails in your laptop, in your safe environment where you have the debugger. And with that, I'm done.
Thank you.